America's secret ghost jet may soon appear on the USS Gerald Ford, shocking Pentagon officials and rivals. This tailless, triangle-shaped fighter boasts smart skin sensors, laser weapons, and hypersonic speeds of over 6,000 miles per hour. It can even command a swarm of robotic wingmen. Earlier stealth jets seem obsolete in comparison. Has the US Navy just rewritten the rules of aerial warfare? And how will China and Russia react to this invisible predator of the skies? Join us as we unveil the 7th-generation fighter jet before it makes it on the United States aircraft carrier. The sky above the USS Gerald Ford lit up with a bright blue flash as something incredible took place. After nearly a century of struggle, the United States Navy had finally solved one of its biggest challenges. Carrier-based jets could now match or even surpass land-based fighters. For years, aircraft carriers had a major disadvantage. Their jets had to be smaller, lighter, and carry less fuel compared to those launching from land. As countries like China and Russia built powerful land-based fighters and long-range missiles, many experts doubted whether carriers could hold their ground in modern warfare. That changed with the Navy's next-generation air dominance fighter. Unlike the older FA-18 Super Hornets, this new jet brought futuristic technology that had once seemed impossible. It wasn't just a single aircraft, it was the leader of a small team. Each NGAD fighter was paired with autonomous drones, commonly called collaborative combat aircraft. These drones carried extra weapons, sensors, and fuel, following the lead fighter's commands while also making quick decisions on their own. A single pilot could now manage what used to take several people. The USS Gerald Ford's firepower grew even stronger with the addition of the Helios laser weapon system. This powerful 150-kilowatt laser could track and destroy incoming missiles and enemy drones almost instantly. Unlike traditional missiles that could run out, the laser remained operational as long as the ship had power. Most people had no idea how fast this technology was advancing. When an Air Force official revealed in 2020 that a test version of the NGAD fighter had already flown, defense experts were caught off guard. The Navy had been quietly working on this breakthrough for more than 7 years, replacing outdated systems from the 1990s with cutting-edge technology designed for the future. The USS Gerald Ford was designed with cutting-edge advancements in mind. As the Navy's most sophisticated aircraft carrier, it featured electromagnetic catapults that propelled aircraft more swiftly and effectively than traditional steam-powered systems. Its nuclear reactors generated the vast energy required for the Helios laser. The NGAD fighter also looked completely different from older jets. It had no vertical tail fins and featured a sleek triangular design, allowing it to fly in ways that would have made traditional aircraft lose control. Advanced computer systems made thousands of tiny adjustments every second to keep it steady and maneuverable. In training exercises, the results spoke for themselves. Against experienced pilots flying F-35s, the NGAD fighter and its robotic wingmen won nearly every simulated battle. The difference was overwhelming. For countries that had spent billions developing anti-ship missiles to keep United States carriers at a distance, this presented a serious problem. With these new jets, carriers could now operate much closer to enemy territory without fear. For the first time since World War II, carrier-based jets weren't just keeping up with land-based fighters, they were better. This wasn't just an upgrade. As the sun set behind the carrier, the new fighter launched into the night, its silhouette blending into the sky. The aircraft represented a development in naval warfare. What happens when these advanced fighters go beyond the clouds and into the vast darkness of space? Could the next generation of American warplanes be used as spacecraft? Engineers across America are already working on technologies beyond those used on the USS Gerald Ford. While naval aviation advances, the next leap is happening in secret labs. The goal isn't just faster planes, it's aircraft that can move between air and space. These next-generation hypersonic fighters could transform aerial combat. Traveling above Mach 5, more than 6,000 kilometers per hour, they could cross continents in minutes. A fighter this fast could fly from New York to Los Angeles in under 30 minutes, making it nearly impossible to track, let alone stop. Building such an aircraft comes with massive challenges. At extreme speeds, air friction generates heat strong enough to melt standard materials. To solve this, the Air Force and NASA are developing heat-resistant composites that can withstand over 2,000 degrees Celsius without breaking apart. Propulsion is another hurdle. Regular jet engines can't function well at extreme speeds or in the thin upper atmosphere. That's where scramjets come in. Unlike traditional engines, scramjets have no moving parts. They use the aircraft's speed to compress incoming air, generating thrust. Since 2018, the Air Force's Mayhem project has been testing scramjet prototypes, gradually improving their performance. Unlike earlier fighter jets, these advanced aircraft wouldn't just fly high, they could briefly leave Earth's atmosphere. By reaching altitudes above 100 kilometers, they could enter a suborbital path, skipping across the upper atmosphere like a stone across water. This would allow them to strike targets with almost no warning, conduct surveillance from altitudes beyond the reach of anti-aircraft weapons, and even deploy small satellites to restore communications in combat zones. The United States military has been quietly funding this research for years. DARPA has been working on airspace transition vehicles since 2020, focusing on designs that can move between the atmosphere and space without rockets or launch pads. But breaking into space creates new risks. Outside Earth's atmosphere, cosmic radiation can damage electronics and pose health risks to pilots. Engineers are developing shielding and radiation-resistant computer systems to keep these aircraft safe. Fuel is another challenge. Traditional jets can refuel mid-air, but space-capable aircraft need an energy source powerful enough to push them beyond most of Earth's gravity and still bring them back safely. Advanced hydrogen propulsion is one possible solution, providing high energy output with only water as a byproduct. The race to develop this technology is already underway. China is rapidly increasing its hypersonic research budget, while Russia's PAKDP program is working on similar aircraft. Any country that masters space-capable fighters will gain a major military advantage. This also raises legal questions. The 1967 Outer Space Treaty bans nuclear weapons in space, but doesn't address conventional weapons or temporary military operations beyond Earth's atmosphere. This loophole has sparked new debates at the United Nations about the future of space warfare. Even the best pilots would need entirely new training for these aircraft. At hypersonic speeds, decisions must be made in milliseconds, too fast for human reaction times. AI assistance and augmented reality systems would have to predict and respond to problems before they happen. The Air Force is already preparing for this future. Specialized bases are being upgraded to support these hybrid airspace vehicles, with reinforced hangars, advanced cooling systems, and specialized fuel storage facilities built to handle the extreme demands of hypersonic flight. While sixth-generation fighters represent the future of modern warfare, these seventh-generation space fighters are something entirely different. The line between science fiction and military reality is disappearing fast. What once seemed impossible is now just a matter of time. As these jets push the limits of technology, the big question is, who or what will be in the pilot's seat? Behind closed doors in high-tech labs across America, engineers have been building the brains of future warplanes long before a single piece of metal is cut. Before these next-generation fighters take shape, their artificial intelligence is already training in virtual battles against the world's best pilots. AI is no longer just a co-pilot, it is being designed to take over entirely. What began as basic autopilot and warning systems soon expanded to flight guidance and real-time threat analysis. Now, cutting-edge AI can autonomously execute complex combat missions, making split-second decisions faster than any human pilot. A breakthrough came with the Pentagon's Project Maven. Launched in 2017, it began by teaching AI to recognize objects in drone footage. Over time, the system evolved to track multiple moving targets, even through clouds, smoke, and electronic interference. The next generation of warplanes will look unlike anything seen before. There will be no cockpits or instrument panels, just advanced processors, cooling systems, and AI-powered decision-making packed inside a sleek, high-speed airframe. These aircraft will be more like flying supercomputers than traditional jets, controlling weapons, sensors, and engines with machine intelligence. The way these planes are built is also changing. In factories across Nevada and California, massive 3D metal printers are already shaping experimental aircraft parts. These machines create complex designs layer by layer, using titanium and carbon fiber, making structures that were previously impossible with older manufacturing methods. This advancement accelerates production at an unprecedented rate. In the past, developing and testing a new design could take several years, involving extensive prototyping, manual adjustments, and countless trial and error phases. Now, with advanced automation and AI-driven simulations, the entire process can be streamlined, reducing development time to just weeks. Engineers can rapidly iterate designs, test performance in virtual environments, and refine prototypes with real-time data, allowing for faster innovation and deployment. Engineers feed designs into simulations where AI runs countless virtual test flights, refining the aircraft before a real one is built. Only the best designs move forward, ensuring each new fighter is an improvement over the last. Military planners see an opportunity in this rapid development cycle. Instead of producing hundreds of identical jets that risk becoming outdated, they can create smaller batches that evolve over time. Each generation learns from the last, making the fleet smarter and more adaptable. Another breakthrough is the concept of smart skin. Instead of mounting separate radar and sensors, the entire surface of these aircraft will be covered in tiny sensors, turning the whole plane into a flying surveillance system. Traditional jets have blind spots, these will have none, detecting threats from all directions and instantly sharing that data with other AI-powered aircraft. This real-time connection gives AI-controlled jets a major edge. Multiple fighters can operate as a single intelligent unit, responding to threats as a team. Smaller, unmanned drone fighters, built at a fraction of the cost, can fly alongside, carrying extra weapons, scouting ahead, or even sacrificing themselves to protect the primary aircraft. But with AI-driven warfare, ethical concerns grow. Military rules state that a human must have meaningful control over combat decisions. Yet at hypersonic speeds, human reaction time simply cannot match AI decision-making measured in microseconds. The Navy has formed an advisory board to address these concerns, ensuring AI follows rules of engagement and minimizes unnecessary harm. However, programming a machine to understand restraint and proportionality remains an unsolved challenge. Technical hurdles also remain. AI-driven aircraft require immense computing power, generating extreme heat. Scientists are exploring quantum computing and advanced cooling systems to keep these machines running efficiently. And while AI has mastered strategy games like chess, aerial combat is far more unpredictable. Training AI pilots in massive simulation environments is key to sharpening their combat skills. The combination of rapid manufacturing and AI autonomy is reshaping aerial warfare. The nation that perfects this technology first will gain an overwhelming advantage, one where warplanes don't just fly, but learn, adapt, and improve with every mission. Even the most advanced fighter jet loses its edge if the enemy spots it from miles away. But what if these new warplanes could completely disappear even from human sight? The most surprising thing about the next generation of fighter jets isn't what they have, it's what they don't. The familiar vertical tails that have defined military aircraft for over a century are gone. Sharp edges and visible engine intakes are missing too. Instead, these jets have a smooth, flowing shape that looks strange to experienced pilots. With soft edges and no clear front or back from certain angles, the design defies traditional aerodynamics and stability rules. It resembles a flying triangle more than a conventional aircraft. This groundbreaking transformation is the result of decades of advancements in stealth technology. The first-generation stealth aircraft, such as the F-117 Nighthawk, relied on angular surfaces to scatter radar signals. The B-2 Spirit bomber improved upon this by incorporating smooth curved contours to further reduce detectability. Today, the most advanced designs push the boundaries even further, striving for near total invisibility to enemy radar systems. Older planes needed vertical tails for stability, but those tails made them easy radar targets. Engineers replaced them with an advanced flow control system originally tested on the B-2. Instead of stabilizers, hundreds of tiny air jets adjust the aircraft's balance in real time. A computer makes constant corrections, ensuring smooth flight without traditional control surfaces. The aircraft's skin also enhances stealth. Radar-absorbing materials are built directly into the structure, making them more durable than older coatings that wore off. Some sections even contain carbon nanotube layers that absorb radar signals and release the energy as harmless heat. Heat detection is another challenge. Fighter jet engines produce extreme heat, making them easy targets for infrared sensors. New designs cool the exhaust before it leaves the aircraft, then spread the remaining heat over a wider area, reducing their infrared signature. This makes it harder for heat-seeking missiles to lock on. Beyond stealth, these jets are built for adaptability. Older fighters were rigidly designed, meaning upgrading one system often required redesigning the entire aircraft. The new generation features modular components, allowing engineers to swap out weapons, sensors, and avionics quickly without major overhauls. This approach cuts costs and extends the aircraft's lifespan. Instead of waiting years for a completely new model, militaries can upgrade existing jets in weeks. Experts estimate this could reduce costs by 30 to 40% compared to today's most advanced fighters. For radar operators, detecting these aircraft is becoming nearly impossible. Older stealth jets had radar signatures the size of a small bird. Today's fighters appear smaller than a marble. The goal is to become virtually invisible to radar altogether. Even spotting these jets with the naked eye is difficult. Adaptive camouflage panels on their surface can change color to blend with the sky or terrain below. While not true invisibility, this makes them extremely hard to track visually, especially from a distance. Every aspect of these jets is built for real-world combat. Critical areas are reinforced to withstand damage, maintenance access points are easier to reach, and vital systems have built-in backups. These improvements come directly from lessons learned in modern warfare. Stealth technology has always been a cat-and-mouse game. As enemy sensors evolve, stealth aircraft must adapt. With flexible designs and cutting-edge technology, these new jets are built to stay ahead, ensuring dominance in future battles. As America leads in stealth tech, others race to catch up. How did a marketing move spark a trillion-dollar power struggle? The idea of fighter jet generations didn't start with military strategists or aviation pioneers. It was a marketing move by Lockheed Martin. In the early 2000s, the company needed a way to make its new F-35 fighter stand out. The solution they came up with was to call it fifth generation, making everything else seem outdated. The term caught on. Soon, military officials, journalists, and analysts worldwide adopted the classification. Older jets were retroactively sorted into generations. The Korean War-era F-86 Sabre became first generation, the Vietnam-era F-4 Phantom was third generation, and Europe's Eurofighter Typhoon landed in the fourth generation category. What began as a sales tactic reshaped global defense strategy. Countries now felt pressured to keep up. When China unveiled its J-20 in 2011, state media repeatedly emphasized one point. It was China's first fifth-generation fighter. The message was clear. China had joined an exclusive club previously limited to the United States and Russia. India accelerated its fifth-generation program. Japan prioritized acquiring such capabilities. South Korea launched an ambitious effort to build its own next-generation fighter instead of buying from abroad. This marketing-driven shift overlooked an important fact. Before generational labels took hold, countries evaluated fighters by their capabilities, not arbitrary classifications. The French Rafale and Swedish Gripen featured advanced technologies that rivaled early fifth-generation jets. Yet they were dismissed as merely 4.5 generation. The United States officially moved towards sixth-generation fighters in 2014 with DARPA's Air Dominance Initiative, securing nearly $1 billion in early funding. By 2020, the Air Force confirmed that a demonstrator had already flown successfully, pushing rivals to accelerate their programs. China responded by reorganizing its aerospace sector, pouring funds into AI and advanced materials research. Satellite images soon revealed remote test sites where experimental aircraft could fly unobserved. Despite economic struggles, Russia pressed forward with its PA-KDP program to replace the aging MiG-31. Officials highlighted its planned ability to operate at extreme altitudes, an apparent counter to United States' interest in space-capable fighters. European nations, unable to match these investments alone, formed cooperative ventures. The UK-led Tempest project partnered with Italy and Sweden, while France, Germany, and Spain joined forces on the Future Combat Air System. Both programs aim to maintain European defense independence rather than rely on American jets. Historically, new fighter generations emerge every 10 to 15 years. Now, the leap from 5th to 6th generation may take 25 to 30 years due to rising costs and complexity. 7th generation concepts might not enter service until the 2070s, marking the longest development cycle in fighter history. Meanwhile, the B-52 bomber offers a different approach. First deployed in 1955, it has been continuously upgraded and could serve for a century, proving that evolution sometimes beats revolution. Lockheed Martin, which started this generational race, continues teasing the future. At its Skunk Works 80th anniversary, a mystery aircraft appeared alongside historic designs like the U-2 and SR-71, potentially America's next fighter. With future programs expected to cost hundreds of billions, international collaboration is now essential. What began as a marketing ploy has reshaped global military aviation, making generational labels a defining factor in national security and defense spending. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.